Hey everyone, and welcome to week 3. This is the third pre-class lecture, and today we are going to be going through multiple regression. And by multiple regression, I mean true multiple regression finally, in that I am talking about regression in which we have a number of independent variables. For the most part today, we're going to be focusing on two independent variables. Towards the end of this lecture, we will talk about cases with more than two independent variables. All right, so to begin this, let's start by talking a little bit about causal modeling. One of the great things about regression and the many tools that we have available to us within the context of regression is that we can make some sort of inference about cause. And when we say cause, we are specifically saying the cause of y due to x. In order to make these statements about x causing y, we have to have some situations, or we have to meet some kind of basic criteria. The first basic criteria that is important when we're trying to, or one, not the first, but the first one to think about when we're talking about regression models, especially regression in the context of how it's often used today, is can we say for sure that x comes before y in time? That is there temporal precedence for x leading to y? So we might have some sort of indice of something that happened to a person at birth. This might have been self-reported when they were 30 years old, but we can use that as a predictor for something right now. So even within cross-sectional data, it's possible to establish temporal precedence even if the data is collected at the same point in time. Alternatively, you can collect data at multiple time points. This means having models that are longitudinal or intensive longitudinal, which is a lot of the types of data that I do, or just simply prospective, which means you take an assessment at one point in time and you take another one at some point in the future. Alternatively, you might have some sort of theory that specifies that X is a cause of Y, and outside of methodological reasons, you can make that case. For example, we might say that impulsivity causes more emotional disruption or more emotional dysregulation, and consequently, X impulsivity causes Y. It gets sticky if you could also say, well, yeah, but the more emotionally dysregulated a person is, the more impulsive they are as well. So you have to have sound theory behind that. Another way to show that X causes Y is through some change in X. So usually when we think about a change in X, what we're thinking about is a manipulation, right? This is our basic experimental model. We manipulate X in some way and we observe a change in Y, or observe if there's a change in Y. It doesn't always have to be a manipulation though. For example, we do know that there are higher rates of impulsivity, or at least certain types of impulsivity, in males versus females. And so X could be biological sex and Y could be some sort of impulsivity. And we could say that your biological sex causes your levels of impulsivity, at least to some extent. And then finally, we might say that the effects of X on Y can be isolated from other types of potential effects from other types of variables. For all of these, we use a causal diagram to understand and explain them. So this is the basic causal diagram for two variables with x1, x2, and y. And in this case, what I want you to think about, and we're going to talk about this in just a second, but we have here a correlation. This path represents a correlation between x1 and y. Then we have a correlation between x2 and y. And then we have a correlation between x1 and x2. This is a basic regression model in which you have two predictors and one outcome variable. What's not depicted in this path, and what's equally important, is that we see that there's shared variability between x1 and y, and shared variability between x2 and y, and shared variability between x1 and x2. But there is also a small portion of shared variability between x1, x2, and y. Sometimes it's easier to look at this using a Venn diagram. So in this Venn diagram, you can see that we have y, and this circle represents all of the variance in y. The blue, pure blue, represents variance in y that is not attributed to either x1 or x2. And then we have the variance right here that is purely attributable to x1. The variance right here in y that is purely attributable to its association with x2, and this variance, which is purely attributable to x1 and x2 interacting to predict variance in y. We'll talk about this area here in a little bit. Then we have this over here, which is the overlap between x1 and xy that has nothing, or x1 and x2 that has nothing to do with y. This also becomes very important because it can lead to some kind of problematic issues within our regression models. We'll talk about those in a second. Let's talk about the regression coefficients that you get when you run these types of models with multiple predictors in there. Let's start with x1. So we have what's called a semi-partial r squared, and a partial r or partial r squared. These various predictor, or these various pieces of the model, are what we get when we're talking about independent associations with various portions of variance removed. The semi-partial r squared is the relationship between x1 and y controlling for the relationship between x1 and x2 right here, and only that. It's actually accounting for 100% of the variance in y as a function of a. And so you wind up having a correlation coefficient that is just this piece of the equation. In contrast, we also have the partial correlation coefficient. Just real quick, the actual correlation between x1 and y includes c, right? And it doesn't include this overlap here. So if we're just looking at the relationship between x1 and y, it would be this whole area with 100% of this piece and 100% of this piece, and that gone. The semi-partial correlation coefficient and semi-partial r squared then wind up being this piece, this percent of the variance of y, assuming all of this is still there and assuming we have not removed any of this. But this does not count. What you'll find is that the bivariate correlation between x1 and y is the highest correlation coefficient that you'll find between these two variables. The second highest is going to be the semi-partial correlation coefficient. I'm sorry, the partial. The semi-partial is actually going to be the lowest correlation coefficient that we'll find here. And it's because we're only looking at this proportion of the relationship between x1 and y. We're removing this, and we're looking at all of the variability in y, including this piece, and we're not accounting for that. So that means that the relationship between x and y, this little bit, is divided by the entire amount. In contrast, a partial correlation coefficient partials out this and it partials out this, and it partials out this, and it looks at A as a function of this. So we're still losing this, which drops the relationship between x1 and y down from what we would see just a simple bivariate, a simple two-variable relationship. But this does wind up being the highest coefficient that you'll find in between these two things. And this actually is what we get when we enter it into a regression model. What you're going to get for a coefficient is A and B. C will not be represented. A and B are a linear function of the relationship or of the variance accounted for in y. That means you can add them together. You can take the variance accounted for in A and the variance accounted for in B, and you can add them together, and that gives you total variance accounted for between A and B. It does not include C, and you know this is an interesting point. You could get the partial correlations or semi-partial correlations for all of these and try to enter those into an equation. But unfortunately, the mathematics do not allow, they actually allow for C to be negative, and so it's nonsensical to try and add this. This is an interesting point because this was something that I had asked as a graduate student, can we find out the true value of C? And you can't, because in some instances the true value of C is negative, and it makes no sense to have negative variance. Remember that variance is squared. So we don't worry about that. All we're really concerned with is the magnitude of effect of A and the magnitude of effect of B. All right, let's keep moving here. So within the context of causal modeling, we have two things that we're primarily interested in. We're interested in the direct effects in regression, and by direct effects we are talking about the relationship between x1 and y and the relationship between x2 and y, and in many cases trying to understand which one of these is a stronger predictor. Now we're going to get, as I said, a linear standardized r-squared, which will tell you if this contributes more to understanding the variance or if this contributes more to understanding the variance in y. However, we have an issue here, and it is called redundancy. And redundancy is due to the fact that x1 and x2 are at least sometimes, or at least partially, related. And so we get redundancy mostly in non-experimental research in the behavioral sciences, and it's because of strong correlations between x1 and x2. We have another, so redundancy means that it can be sometimes difficult to parse out what exactly is going on between x1 and x2. Indeed, redundancy among explanatory variables is kind of the plague of our efforts to understand the causal structure that underlines the observations that we've got. In indirect effects, we have something slightly different. We have, notice in direct effects, we have the direct relationship between x1 and y, the direct relationship between x2 and y, and we just correlate or partial out the variance associated with x1 and x2. In indirect effects regression, which incidentally, there is an article up for you guys to read for this week. It's an article by Barron and Kenny that talks a little bit about the difference between mediation and moderation. And indirect effects in regression is also known as mediation. And so in this instance, we have the relationship between x1 and y and a relationship between x1 and m1. And what we are actually saying is that the relationship between x1 and y is at least partially and sometimes completely due to x1's relationship with m1. In your book, they referred to this as x2. I want to get you guys in the habit of calling a mediator m1 or just m. We do have a problem, though, with mediation models, and that is something that we call suppression. So sometimes we will look at the relationship between x1 and y, this relationship right here, in a simple bivariate analysis, and we'll see that there's a positive relationship. Then we will add m1 to our model, and look at the relationship from x1 to m1. And we can have a couple of different issues happen with suppression. In just your basic indirect or direct effects model, we might see that the relationship between x1 and y becomes negative after we add x2. Or we might see that the relationship between x1 and y becomes negative here. Alternatively, it can become negative here as well if you had looked and initially found a positive relationship between these two. Or somehow the indirect relationship flips signs in one way or another. This happens primarily because there is too much overlapping variance between x1 and m1, and that the only variance between x1 and y that you're finding is, between x1 and m1 or x1 and x2. The only variance that you're finding between x1 and y is a small proportion of variance that can be often spurious in nature or something else. And one of the things that's important to note, we're going to talk about spurious effects here in just a second, but one of the things that is worth noting is that suppression is, sometimes it's a plausible model, especially in homeostatic types of systems where you have kind of biological and social forces and counter forces that are working back and forth, or can have a counteractive effect on each other. So just because you observe suppression doesn't mean it's just a statistical anomaly, though sometimes it is just a statistical anomaly. If you have suppression in your analysis, it is something worth talking about. Rather than just saying like this might be a suppression effect and calling it that and walking away, you should try to provide some sort of rationale for why it might be a suppression effect, if possible. It's not always possible. Sometimes the numbers just aren't there for you. All right, we also have what are called spurious effects or entirely indirect effects. Spurious effects occur when, for whatever reason, the relationship between x1 and y is completely due to variance that's been partialed out of x1 because of adding x2 to a model, or because of x1's relationship with x2. Sometimes a suppression effect is a completely spurious effect. Alternatively, we have the situation where we have entirely indirect effects. This is more rare, but it's not completely unheard of. In the Barron and Kinney article that you're going to read, they're going to refer to indirect effects as a change in this path after adding this variable to the model. That's not always true. Sometimes you have no correlation between x1 and y, and yet there's a correlation between x1 and m1, and a correlation between m1 and y, and there is an indirect relationship between x1 and y via m1 that is not observed in simple bivariate associations. Your book on page 79 gives some examples of this. It's worth going through and reading those. I will say this: if you're going to make a case for an entirely indirect effect, you have to have a good theoretical reason for doing so. And that goes for basically every type of causal modeling that we're going to be doing. All right, final thing we're going to talk about today is multicollinearity. Sometimes you run a model, and this is actually a real model that I ran looking at two different conditions, trying to change alcohol expectancies and then predicting alcohol outcomes. In this case, we had 8 different alcohol outcomes and 4 different alcohol expectancies. The alcohol expectancies were correlated very highly, sometimes as high of a correlation as 0.8. And when you put all of these in the model, what you find is that only one of those expectancies predicts alcohol outcomes. The rest of them are all non-significant. In each individual models, if you just look at liquid courage, conditioned to liquid courage to alcohol outcomes, we see significant effects. Through here, significant effects. Through here, significant effects. It works, but when you put them all together, only one of them works. So the question is, how do you handle a situation like this when you know that all of these things are important, but they're just so highly correlated that you can't look at them all together? Another issue that came out here is we had 8 different alcohol outcomes that were all highly correlated, though some of them were different in what they were trying to get across. Some of them were related to alcohol problems, where some of them were related to consumption, and some of them were related to binge drinking. So there's a few different ways that you can do this. You can combine all of these into a single variable just called expectancies, right? You could do the same thing with your alcohol outcomes. You can also run a separate analysis for each one. I'm going to point out a serious problem here. If I were to run a separate analysis for each one of these, that is one analysis for liquid courage to each of the alcohol outcomes. That's 8 different analyses. I did that. If I were to do that 4 times, that is 32 different analyses. If you were to do a pairwise correction, because you're doing 32 different types of analyses, all of a sudden your p-value becomes extremely, extremely small. Your criteria, your cutoff criteria is, what is it here? 0.05 divided by 32, 0.0015625, which, I mean, that is a steep criteria. Not a terrible criteria, but something that it has to be thought about. The alternative approach is to do something like this. We formed a latent alcohol expectancies variable, and we're not going to talk about this. This is like in chapter 13 of your book, but it allows us to use all of these alcohol expectancies as a single variable. And then we wound up doing 8 different analyses. And in this case, we use bias-corrected Bayesian credibility intervals. And so anyway, that is one way to handle multicollinearity. We're going to talk about this in class. Another way is to do something called hierarchical regression. This is another thing that we're going to go through in class this week. Actually, I think we do that in chapter 5, so maybe not this week. But it winds up, it is an empirical way to find the best predictors for a model. And that is it, guys. I will see you all on Thursday this week.